Good afternoon. I'm Becky Jaramillo from the National Institute of Aerospace and a representative of NASA Langley Research Center. And we're here at Wallops Flight Facility in Wallops Island, Virginia. Now that's up the eastern shore in Virginia. I'm near Chincoteague. Some of you may have heard of that. I'm very close to the Virginia-Maryland border. But we're here with a guest today, Mary Beth Wusk. Mary Beth, tell us what's going on in this room and why are we here at Wallops anyway?
Well, thank you for having me. So we're here to demonstrate technology of inflatable heat shields. Now, back in 2009, August of 2009, we had our first successful launch of the inflatable reentry vehicle experiment. So this is a follow-on to that mission. And what we're doing now is we're advancing this technology by taking it to higher temperatures. We have a more aggressive trajectory that we're going to be flying for this flight. We also have a thermal protection system on this article that we didn't have last time. So the idea is we're making these inflatables that we're able to bring back hardware from any place that has an atmosphere and bring it back safely. It's sort of a replacement for the rigid air shells.
Oh, so tell us more about what you mean by the trajectory and exactly what that's going to do for this particular mission.
Well, for this mission, we're flying to an altitude of about 280 miles. Wow. And we're flying on a Black Brand 11, a three-stage launch vehicle. And we're doing that so we can achieve high temperatures, during the reentry, much more high, about 10 times higher than what we experienced on RV2.
Okay.
And by doing that, then we can demonstrate the flexible TPS, the thermal protection system that is over the article. So a little bit more about the article. Maybe I should back up and explain that.
Yeah, really. We have this thing that has a thermal protection system on it, but what is it anyway?
Right. So this article expands into about a 10-foot diameter heat shield that is stowed, and the stowed configuration is about within 19 inches inside of a 22-inch shroud. So it's really very compact, and once we launch, we inflate, and then we can bring back more hardware. Now the rigid, you're kind of limited by the shroud of the launch vehicle. So
I'm going to stop you there for a second and say, okay, let me repeat that to make sure I'm right. Then you have a rocket that has a 19-inch diameter in it, or a 22-inch, right?
22 is the shroud, but we have to be a little smaller to fit inside.
To fit inside the rocket. So you're telling me that you're going to be able to inflate this vehicle to 10 feet from something that will pack into a tube that's about 19 inches?
Yes, absolutely. We've spent a lot of time working on packing and storage, and also making sure that the materials can handle, the compression over a long period of time, and then also handle the heat rates that we'll be experiencing. This is the same diameter that we did on RV2, but again, as I said, we're going to like 10 times the heat rate. We're expecting temperatures to be somewhere in between, I think, 14 and 19 watts per centimeter squared. To give you an idea of what that means, for what we did on RV2, the temperatures that we experienced, it would have felt like if you were to burn your hand after 10 seconds, on a light bulb or something like this. Okay. For this, it's experiencing temperatures that you would feel out of a blowtorch. I mean, it's much higher. And we'll be experiencing that for about 30 seconds during the reentry.
So at a height, an altitude of only 280 miles above the surface here, you're going to get that kind of heat for reentry.
Yes, absolutely.
How does that compare to the reentry that a vehicle would have to face if they're landing on, say, Mars?
Well, that's sort of our next step, and the idea of this project is to be a step in the technology development. You have to start weighing your risk with technology development. So we've done a lot of ground testing to make sure that we've done everything we can on the ground, but that's coupon level, it's small. You're not really in a relevant environment. So our next step was to now take it to a sounding rocket and then to demonstrate this capability on board. And then ultimately, we like to take it to something in a larger vehicle, something similar to like the Taurus 2, and demonstrate that we could bring things back from space station. And once we get to those levels where we're at, when I'm saying for this launch, we're somewhere around 14 watts per centimeter squared, we're going to have to be going up to about 30 watts per centimeter squared. So
that's pretty hot.
Yes.
Yeah. So the big difference between RV2 and RV3 then is the height that you'll be launching it to, and the actual thermal protection system that you're testing.
We also are doing something new on RV3 that we didn't do on RV2, is we have a center of gravity offset system. So you'll be hearing more of that from Nathaniel Miller later, where we're actually adjusting it, and we're looking at the controllability of the vehicle itself, how the system responds to that maneuver.
Well, Mary Beth, you seem to know a whole lot about several of these systems. Exactly what is your role in all of this mission?
Well, for this mission, I'm the HIAD project manager, and HIAD is hypersonic inflatable aerodynamic decelerators. But IRV3 is one of the projects beneath me, and the project the project, the HIAD project. Sorry. But actually, I was the IRV2 project manager, so I'm fairly well versed with the experience on IRV2. So, along with this flight project that we're doing, like I mentioned earlier, we're doing all sorts of ground testing as well. So, I'm responsible for those activities too.
So you have a pretty big team here with you then.
We do. For this launch, I think we'll be having about 40 people out here supporting the effort. But for the whole HIAD mission as a whole, we have about over 100 people that are supporting this across the agency, and as well as contract support as well. Wow.
So it's not just a 1 or 2 person piece of this. So tell me what in the world brings somebody like you to be a project manager? You know, what's your background, your career path? How in the world did you get here?
Okay. I asked myself that question. I've been out at NASA for 22 years.
And you're at NASA Langley?
Yes, at NASA Langley. I've been working on aircraft. I started my career with aircraft instrumentation, and then I moved to the space side of the house. And to me, I've always liked working on tangible products. And this is an ideal demonstration of that, where we've built it, we've designed it, we built it, we're launching it, we're getting the results. So I'm interested in that sort of thing, so that's where I came from. My background is physics and electrical engineering.
So what advice would you give somebody who wanted to be sitting in that seat in a couple of years or in 10 years? What would you want to tell them?
Well, it's not always easy, especially during the academic part. So just hang in there, get as much hands-on experience as you can, because the more time you have with hardware or working with the software itself, I mean, you're more valuable to the team, and be willing to just do whatever is needed to be done to get the job done to help the mission be successful.
So how do you feel today?
I'm excited. This is my third launch from Wallops.
This is my first one, so I'm kind of excited too.
I'm very excited. We'll be doing our dry run, our mission rehearsal tomorrow, so the rest of the team will be out here. We have a whole group of students that I'm very excited about who are going to be doing some ambassador work for us.
Good.
And so coordinating that has been a little crazy at times. And just the excitement of what's going on here and what could happen once we're successful is very exciting for me.
Right. I'm going to go back to something you just said. You talked about a test run. Now, you're not actually going to shoot a rocket off for that test run, will you?
For which test?
For tomorrow, when you do your test run tomorrow.
Oh, no.
So explain to our audience what a test run is then, because when we think of test runs, we think of the Indy 500. They're running around.
So a mission rehearsal is just to allow people on the console to be familiar with what their roles and responsibilities are, and we go through the whole sequence, the pre-flight test for the mission. We will be going through we will be communicating with the launch vehicle. We'll be communicating with the range services, but we will not be launching the rocket tomorrow.
So communication is an important part of this then.
It's huge, and everybody has to clearly understand what their roles and responsibilities are. As you know, our launch window is fairly small.
It is.
So, we have constraints to make sure that we're all ready and we're not the long pole in the situation.
Right.
I mean, we have enough other issues, potentially, boats in the rain, in the impact area, that we have to make sure that's clear.
Right.
So the planets have to align for us to be ready to launch on time.
We're going to talk to a flight director, the test director from Wallops later on this afternoon. So we'll find out a little bit about the logistics from her point of view. I really am glad to hear that you practice, just like we tell our students, we tell people they have to practice things. You don't just go in and make it work the first time. So
that's absolutely right.
So Mary Beth, thank you so much for being with us. Is there a time maybe we can pull you back in at the end here, and we may have a couple more questions for you?
Sure,
I'm sure you're going to be around.
I'll be here.
All right, thanks. Mary Beth Wusk, and let's look around us a little bit and see what we have, where we are in mission control here from Wallops Flight Facility.